Okay, so we're going to do volume today using in calculus, AB. And the idea of volume is, for us, we're going to talk about two main things, and we have another technique also. We're looking at something called discs and washers. And discs and washers are kind of counterintuitive to what we think sometimes. We think of sometimes a CD disc versus a disc we're talking about. The disc we're talking about is like a frisbee disc. If you think about a frisbee disc, it's like nice circular frisbee, and it's solid all the way through for the most part. And what we're going to do here is we're going to build a volume using a bunch of these discs, and we're just going to end up stacking them on top of each other. And when we stack them on top of each other, we'll end up, instead of having a 2D object, we're going to end up with this 3D kind of object here. Okay, and we end up figuring out what the volume of the shape is. Now for us, let's start with something kind of basic. I want to show you guys some visuals. And I'm going to share here. I'm going to show you guys what we're kind of planning toward. And this is kind of what we're aiming for. We're trying to get a object here, for instance here, a line. And this is just a y equals line. And we are going to rotate this a couple times. Sorry, change this a couple settings here. Give myself 4, actually. And we're going to rotate. Let's reset that. We're going to rotate this around the x-axis. And we're going to rotate it all the way across. And that'll give us this kind of circular shape. But on a basic level, if I use 4, that's not going to be a great approximation. But if I increase the number of washers here, disc here, that's a 10, this would better approximate my curve. If I change this to 100, this would be even closer. If I change this to 1,000, this would be even closer than that. So our goal is to find this volume rotating around a given axis. In this case, y is equal to 0, our x-axis. So going back, let's talk about how we're going to do that. So I can take over here. Let's take back my axis. So what we're going to do, let's come up with an equation, something like y is equal to x squared of x. So we know squared of x graph does this curve, like we saw in our example, when, just some easy numbers, when x is 0, y is 0, when x is 1, y is 1, when x is 2, oh, sorry, let's not use 2, let's use 4, y is 2. Some easy examples here. 1, 1, and something like 4. That'd be like 2. Okay. And we are going to find the volume. So far, this is just a 2D shape. This is just flat. And we've called this area before. The way we found area here was cumulative change. We took an integral. Let's go back to the idea of area. Because we took the integral, let's say from 0 to 4, of f of x, which is the square root of x, times a little bit of dx. And if I solve for this integral equation, this would give us the area underneath this curve. Now, how did that work out? Well, the idea is from a to b of f of x, which is your y value, and dx, which is a little bit of x. So this is our base, and this is our height. Okay. So when we were talking about area before, how did this work? We took a little bit of dx, we multiplied it by the height there, f of x, and that gave us one sliver. And then we went ahead and we added another box next to that with a little bit of dx, and then followed by another box after that. And that's the cool thing about our integrals here. We were adding up all these little small changes. Base times height, little small rectangles. We thought about that as Riemann sums. But when we do integration, we have an infinite many set of rectangles because our dx is a very small section of x, so small it's practically zero. So we can fill in infinitely many. So what we're going to do now, we're going to change this 2D object to a 3D object into a volume here. And what happens is we're going to take it, looking back at the top, and we're going to spin it. And it's going to give us a mirror reflection on the bottom. And it'll give us a little circle through rotation. Let's spin it. Okay. And we're going to do this infinitely many times. And the integral is going to add that up for us. So our basic idea is somewhat very similar to what we did before. For area, we added rectangles. But for volume, we're going to add circles. Now let's look at a geometry. If I'm looking back in geometry, looking at area, the area of a rectangle, it was just base times height. Okay, so we call this f of x, which was my height, and our base, which was a little bit of dx, so base times height. But the area of a circle as we revolve around the y-axis, sorry, the x-axis, I'm sorry, x-axis, the area of a circle is pi r squared, where r is this radius. But I'm not going to draw the radius that way. I'm going to draw the radius going up. So this is my r, which is also, in this case, going to be my f of x. So if r is f of x, to find a circle is really just pi f of x squared. Now, let's actually try that. Looking at the radius right here, at 1, okay, what would the area of that thin, very thin slice circle be? If I'm looking at area, let's be pi. Oops. Let's go ahead and give me some space down here. Draw that one more time. Oops. Draw this like that. At 1, what would the radius of the circle be? Well, that's also the height of the function. It turns out all these problems that we're doing, our radius, in this case, is going to be the height of the function. Well, f at 1 for the square root of x, which is square root of 1, is just going to be 1. Sorry. Close the window. Way of edit it. Okay. So if f of 1, which is my y value, the height of my function, is also the radius of the circle, because that looks like it's the radius of the circle. How do we find the area? Well, that's just pi r squared. Area is just pi r squared, which is pi f of 1 squared, which is square root of, sorry, jumped ahead there, pi square root of 1, which is just 1 pi. But be careful, this is just the area. And how do I find volume? So that's back to geometry again. To find volume was this essential idea, is the area of the base times height. This is the area of the base times height. Now, to just show you some easy examples of this, if I had a cylinder, we would say it's the area of the base, and we would multiply it by, multiply it by the height. So area of the base times height gives me volume. What if this was a prism, a rectangular prism? Some idea? Oops. We find the area of the base. We multiply that by the height. So to find the volume here, what type of thickness do we have? Well, the type of thickness that we have on this problem is a little tiny sliver. And we do that in calculus by multiplying by a little bit of dx. So to find the volume here, the volume is area of our base, which we said was going to be pi square root of 1 times a little bit of dx. But dx isn't dx infinitely small, so super small. So isn't that practically nothing? And that's true, because it's a small sliver, but with enough slivers, as I build up my layers, they'll add up together to give me the full volume here. So let's write out our equation. So to find the volume of a object being rotated, this is our problem. It's going to be the integral from a to b, our starting and ending value of pi r squared times a little bit of dx. So this is our basic idea. We're going to go ahead and add to this. So the integral from a to b of pi r squared. And pi r squared is just a circle. So it's area times a little bit of height gives us our volume. And since these are small slivers, the integral, idea of integral is a cumulative change. That means we're adding up all the slivers together to end up with the full volume. Okay. So just to recap, to find volumes in calculus, when it comes to rotating, we have two main types. We have something called a disk and a washer. What we talked about what a disk was. A disk is a solid shape. What we'll go over next time is a washer, and a washer is just like at a hardware store, there's a hole in the middle. Okay? And we'll worry about that next time. But today, very simply, to find the volume, we're gonna say, hey, if I rotate around this x-axis here, there is no hole in the middle. It's gonna be this solid, like yam-looking thing, or cone. And to find that, it's just adding up circles, pi r squared. Well, to rewrite this, for us, from a to b, our pi is a constant, so you can write it on the outside. And our r is actually our function. We're gonna square it and multiply by a little bit dx. So to find the volume of our example here, so let's talk about our example. Our example was f of x equal to the square root of x. The graph square root of x looks like a sideways parabola. And I want to find the area between a and b, where a is 0 and b is going to be 4 and 0. And if I want to rotate, I'll rotate around the x-axis. That means we're going to be rotating this way, which gives me a mirror reflection. This gives me a nice, easy circle with the radius of the height of the function, f of x. Okay. So to find the area of a circle, that's really pi r squared, which is pi f of x squared, because it's just the area of the circle with the radius of f of x. So pi r squared. And to get volume, we have to multiply this by a little bit, a sliver of dx, a little sliver of dx. So that's how we end up with this equation here. So the volume is pi, because it's a constant, between a and b, which is 0 and 4. F of x, we said, was the square root of x squared dx. And all you do now is take the integral. That's simplified integral. I can do something with a square and the square root. They cancel out, so it's pi. And it goes from 0 to 4 of x dx. Power rule, pi x squared over 2 between 0 and 4. And we just plug it in. Pi of 4 squared over 2 minus pi 0 squared over 2, which is just 4 squared is 16 divided by 2 is 8 pi. That's my answer. Okay, let's do one more example. And let's do something. Y is equal to, let's say x squared. And we're going to go from A is 1 and B is 3. Okay, let's draw that out. The function of x squared is plug in 0 is 0, 1 is 1, 2 is 4. Actually, I'm going to run out of room here. Let's change those marks a little bit. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Okay. 1 is 1, 2 is 4, and 3 is 9. Okay. And we are going to rotate this about the y is equal to 0 axis. Okay. So if I do that, let's draw one circle. If I draw one circle here, rotating this way, you end up with this nice circle here. And it would end up causing us to have a mirror reflection. Oops, nope, not the right tool. Going this way. And in the end, oops, not as pretty as I wanted it. But one more time. With a circle, yes. Okay, we end up with these little cones that come out. Okay. So what main shape do you see here? You should see a circle. So we're going to add slivers of circles. So without actually using the formula, it's just really volume is pi r squared with a little bit of dx for volume. Remember, this area times a little bit of width gives us volume. And from A to B, that's going to tell us when to start and stop the problem. So volume is equal to the integral. In this case, we say we want to start at 1, stop at 3. Start at 1, stop at 3. So the first number is going to plug in is 1. Last number will plug in is 3. Pi is a constant. What's the radius? Well, the radius is literally just the height of our function. In this case, it's going to be f of x. And f of x is the same as y, which is going to be for us x squared. So x squared, pi r squared. Multiply that by a little bit dx. And that is the setup. Again, we're just adding circles together. Circles with a little bit of width. That gives us volume. So volume is equal to, let's take the integral of x to the 4th. That's x to the 4th. So power rule, x to the 5 over 5 between 1 and 3. So the volume is pi 3 to the 5th over 5 minus 1 to the 5th over 5, which gives us some crazy number here. Pi 243. over 5 minus 1 over 5. Okay. And whatever number that is, some calculated number, that's our volume. So what if this object changes? Well, if I give you, let's say, something like a sine graph, and let's say between 0 and pi, let's include them. Sine graph looks like that. And if I rotate it, it just looks like a lemon in this case. So rotate this way, you end up with these little circles. Well, same thing. We're adding up circles. So the volume is integral of pi r squared with a little bit of dx. So the volume is between 0 and pi of pi. Sorry, let's put the pi outside. Then r squared, which is the radius, which is just the y value, which is just f of x, which is sine x squared. Give a little bit of dx. That's the setup. We can't do that sine squared problem. We could do it, but it's going to take us a lot of work. Remember the integral sine squared. We have to use that power reduction rule. The last one real quick is, what if I change the axis of rotation? What if I give you, let's go back to an easy problem. Let's go back to x squared between, let's say, 0 and 3. Oops. And we're going to rotate about y is equal to -2. Let's draw that quickly. The graph x squared goes up like that because it's a parabola. And our y is -2 is actually down here. So what happens here? Well, if I try to figure out what my circle would look like, to get from the axis of rotation all the way to my graph, that's a long walk. Well, how'd you end up with that walk? Well, if this was f of x and this was -2, to find the distance between two objects, we subtract it. So the r here is f of x, or y here, minus -2, which turns out a negative becomes an adding problem. So wherever my function is, I'm going to add 2 for that radius. Let's see if that makes sense. Let's pick another point. Zoom in here. I can't zoom in. Let's pick another point here. This part's f of x, right? Don't we have to add an extra +2 because we're 2 spaces away? What if I pick a point right here? That's f of x. We're going to add 2 again. So all the function is just the y value +2, and that's our radius for a circle. Let's go ahead and draw one circle. And then it turns out our flare is going to go the other way. So something like this. Okay. So in this case, we have this like pot-looking thing. So to not overthink the problem, we're just adding circles. Let's go and talk about the volume now. The volume, again, is adding circles. Integral of pi r squared times a little bit of dx. Underneath the parentheses. Well, what's the radius? We said the radius was the function +2, because if we subtract the differences of the y values, that ends up negative becomes a +2. So pi integral of, in this case, x squared +2 squared. That's my radius, dx. That's the setup. Now here is an easy rule to figure out the radius. It's always upper. It's always upper minus lower. That is just the general rule. Why is it upper minus lower? Well, upper minus lower, whoops, that's wrong, lower. The lower is this axis of rotation here. Because upper is the bigger number. You take a bigger number minus a smaller number will give you a positive difference. You could write it as an absolute value, but it's actually easier for everyone to just say upper minus lower. Even if I give you a function, let's do the same function here. And let's say if I rotate y is equal to positive 2. So this graph would be rotating the other direction, going up, and it would look like this. In this case, it would be upper minus lower. So the r value here would be 2 minus f of x. Okay. All right.